Can you hear me? Is the mic on? Yeah. All right, shall we get started? I thought it was supposed to be warm today. It doesn't feel warm. All right, homework 2 will be up after class. I want to show it to the TAs first and make sure that they're okay with it. So it'll probably be about 11 o'clock. It'll come up. We'll look at it a little bit today as well. There's 6 functions. Each function is kind of on the order of a question of the day. And then there's a driver function, which is mostly written for you with a couple of elements labeled fix me that you need to replace. How many of you read the article over the weekend? You did, huh? Okay, all right, good. So I'm going to give you some sample data, and you're going to compute these meal indices from these sample data for a bunch of students. That's what the project is. It's interesting because it has a lot of the sorts of behaviors we've been covering in class so far. It's a lot of iteration, a lot of scanning, a lot of sorting, and that kind of thing. So I'll review the outline in class today. I'm shooting for exam 3 on April 15th, which is like a week from this Friday, right? So it's like 2 weeks, almost 2 weeks from today. And then, of course, there's the final exam on Friday, May 6th. I haven't decided on homework 3 yet. I think homework 3 is going to be really short, probably be something object-oriented, just because that's what we're talking about now, and it'd be good to have a little bit of an exercise doing something like that. I just haven't thought about it much yet. And the final, of course, is May 13th from 3 to 5 p.m. Okay, so that's sort of what we have going on ahead of us. Let's take a look at what homework 2 looks like. So we give you the general layout of homework 2. You're going to open a file that contains a bunch of card swipes in the dining hall. And you're going to read in each one of these events, one at a time, and you're going to process each event once. So this is not a situation where you're going to read in a whole file and then do some computation on it. You're going to do this in what's called online, in what we call in an online way, meaning that you're going to read one element, you're going to process it, you're going to throw it away. So, and the reason we do this is because if you were to have all of the data for, say, 4 years of meal swipes here at the university, there's, I think there's 900,000 meal swipes a year or something like that. The data file that I'm giving you is for 1 semester. It's fairly large. Now, it's fake data, but it's still on the order of what it would be for a semester, a fall semester here at Iowa. So it's pretty large, and probably not good idea to read it all into your Python environment into a big list and try to deal with it. So we're going to deal with it one at a time. It's called online processing. So here's what an input meal swipe might look like. It's a comma separated value format. Is everybody familiar with comma separated values? It's what you dump from Excel. If you had Excel cells, then this line here would be one row of an Excel file, and the commas separate the cells. So the first cell would contain this date and time. The second cell would contain this identifier, and the third cell would contain this location. So the format here is date and time is one field. This is the student identifier, and this is the location, which is, of course, fictional. Okay, everybody get that? So you're going to get a file of these, a couple, 90,000 of them or something. I forget how many there are in the file. And you're going to, oh, sorry, I messed up the slide. You're going to take in part of, the first thing you're going to do is you read in each one of these, and you're going to turn it into a format that looks like this. So this is a dictionary. It has 3 keys: location, time, and student identifier. You'll notice that the location is just like it appears here. The student identifier is an integer, so we lose that leading 0 because it comes in as a string, and when you convert a string with the leading 0 into an integer, the leading 0, of course, goes away, and you just get the integer part. That's okay. We'll work at the end of this, when we're ready to dump it again, to produce the leading zeros here as well. And then the harder part here is in the middle of this, you have this time value or key, and the value is an object of type datetime that has these parameters. So this is the way it prints out the datetime modules, datetime object, an instance of it. And if you think, I mean, if you look at this and just sort of eyeball it, that looks like a year, that looks like a month, that looks like a day, and that looks like an hour and a minute, right? So pretty clearly there's a correspondence here. Now, to do this conversion, dealing with dates is hard in any language. One of the worst things you could have to do is write a package or library that would compute things like what day of the week is August 22nd, 2015. What day of the week is, how many days are there between August 22nd, 2015 and December 1st, 2019? These kinds of things seem easy, but they're actually not. For one thing, you have to deal with leap years, and leap years are hardly as easy as you might think they are. You get them every 4 years, but not on the hundreds, but every 400 years you get one, and there's all this kind of weird stuff going on. Then you have leap seconds that you add every once in a while, and those things really mess up calculations across year ends. So dealing with dates, converting something like this into and then comparing it to some other date, which is what we're going to have to do, is very messy. Fortunately, you almost never have to do this yourself. In Python, there's a really and in most languages, there's a really excellent library for handling dates and times, and it's the module called datetime. So you will use the datetime module, and in particular, the object called datetime. We're going to talk about objects. We started the other day. So you're going to see objects today. So you'll use datetime objects to represent dates and times. And that means you have to be familiar with that datetime library. And in the code, you'll see that there's a URL for the Python documents for the datetime library. My advice to you is to read it carefully first before you even try to start. So you have to learn about the date and time library. So as you process the event, so remember we're going to take in an event, we're going to do something with it, we're going to throw it away. We're going to maintain what's called a queue, or a list, essentially, of meal events. One queue for every dining hall location. So here we have an event in the Barnett Cafe. And in the Barnett Cafe, any meals that were take place there, I neglected to mention that the file is in temporal order. So the file that you'll get will be in order from the first meal to the last. So you process each one, and when you get a meal like this one, you're going to say, oh, this happened in the Barnett Cafe. I'm going to put this event at the end of the list of meals in the Barnett Cafe. So I'm going to, for every location, like the cafe, there's going to be a list of meals that take place there, and they're going to be in order from first to last. But the trick here is I don't want to store all the meals there because the meals could be many. I mean, there's going to be a lot of meals. I don't want to store them all in Python. What I want to do is just keep a window of those meals that corresponds to a certain time interval. And the time interval is a parameter that's given to you at the beginning. So for example, if I would like to keep a time interval of 4 minutes so that I have all the last 4 minutes of card swipes, when I pull in this card swipe and I add it to the Barnett Cafe queue at the end, I'm going to remove any events from the beginning of that list that are older than 4 minutes from the start of the last event. So think of this, all the events in the Barnett Cafe stretching out in temporal order, and I'm going to maintain this list, which is like a sliding window of 4 minutes of time. So that's the way you should think about it, sliding minutes, 4 minutes of time. So the sliding window is that fixed interval viewport. Now the length of the list may fluctuate because there will be peak periods when there are a lot of meals within 4 minutes, get longer. And then there will be periods when there's nobody in the cafeteria, it may even go down to 0, like nothing happened in that 4 minutes. So you're going to keep this thing dynamically as you read in events. And moreover, you're going to keep many of these because there's many dining halls. So you're going to maintain all of these lists in parallel. I give you this whole list of dining events, but they're in different places. And you don't go eat with somebody and they go to one place and you go to the snack shop. You both go to the same place. So you're going to have to maintain these lists independently. All right? Does everybody sort of get that idea? So I'm trying to give you the big picture here because then we'll look at the template file and I'll explain a little bit more of how to go about it. All right. Whenever I add a meal, so let's say I read this in, I add it to the sliding window for the Barnett Cafe. Whenever that happens, I have to update the count of meals that people take together. So let's look at it this way. This meal that I'm adding is for this particular student. And let's say there's 3 other meals in that sliding window within 4 minutes of this meal. Then I have to add to this student 1 meal for each of the 3 other people. Because for every student, I keep track of who they eat with. How many meals did I eat with Ben? So if I'm this student and Ben's record is in the interval, I have to add 1 to his record for me, and I have to add 1 to my record for him. So I have to maintain this symmetric count of meals taken together, where a meal taken together is the fact that both of you appear in the same sliding window at one point in time. So as I add a person to the sliding window, add an event to the sliding window, I flush anything that's out of date from the end of the window, and then I update everybody's counts to recognize that new meal. All the people in the event in the window already, they get a new meal with the person that's been added, and the person that gets added has a new meal with each of the people that were in the window already. Does everybody get that idea? So this is the basic processing that's going on. We're going to add a few little more complications. At the end of every week of processing, we want to update the student's meal index. Because at the end of the day, what I'd like to know is, at the end of week 1, what is student X's meal index? At the end of week 2, has it changed? At the end of week 3, has it changed? So the meal index is a cumulative measure over the course of the semester, which grows monotonically. When you have your very first meal, when you first show up freshman year, you don't know anybody. So you'll have a few meals here and there with random people, perhaps. But as the weeks go by, patterns start to emerge, and the meal index should grow and give us a sense of your social network. All right? So every week, which I define as starting on a new Monday, whenever I get to a new Monday, I have to stop my processing, I have to compute everybody's meal index, and I have to keep it somewhere so I can output the whole stack of M indexes at the end of the day. So I'm going to store each student's M index in a growing list of M indexes indexed by that student identifier. So for every student, I'm going to keep their list of M indexes by week. Week 0, week 1, week 2, week 3, week 4. And then when I'm done processing everything, I'm going to use that data, I'm going to dump it out in a comma-separated value format. So this is what the output file will look like. You'll have the student so we have a header, student identifier, and then every start of a new week. And you'll notice here, this week starts on August 23rd, this week starts on August 25th, then September 1st. So this is not a full week. In fact, the dining hall, let's say, opened on what would this be, a Saturday morning, because the 25th is a Monday. So fractional weeks at the beginning and at the end, when we're done processing meals, you have to deal with those cleanly. So I've got this header to this file that gives me the column names, student identifier, week 1, week 2, week 3, week 4, week 5, and so on. And we can see this student didn't eat any meals with anybody, right? Maybe he just went and ate when the dining hall was completely vacant, or maybe he didn't eat any meals at all the first 3 weeks of classes. Then he had one sort of fairly regular partner, then 2, then 3, and it grows very slowly. Whereas this guy down here, he starts out with 0 like everybody, but he's making new friends, and his meal index is getting deeper and deeper as he goes. Okay, so let's take a look at what this might look like in the real world. So I provide you with 2 test files. The first test file is the full data file that we've been looking at here. You can see the dates starting on the 23rd of August of 2008 at 1 minute before 8 a.m. And it's in Ruppy Hall, and then the other places are, you can see other places. It's like 8 or 9 different sites. And as I scroll down here, this file is actually quite long, and there are 903,000, nearly a million records. Now, I don't suggest that you write your code and immediately try to run it on this file, because it's going to fail. Even doing this on my desktop, which is a fairly fast machine, takes some time, minutes. Right? You're going to run this, you're going to do all the calculations. It takes minutes to run it. So I've also provided for you a test file with exactly 20 records in it. And they're just the first 20 records of the data file that you'll otherwise use. If you can get through this file and produce a meal index summary file, you're in pretty good shape, and you should be able then to either try the full file or just take a longer set of lines, maybe the first 1,000 lines of the full file, and try that. So this homework is going to test your ability to debug stuff. You're going to have to take it a little bit at a time, because you can't just write the code and then try it on the whole file and assume it's going to work the first time. It's not. It's quite tricky, especially when you get into sort of timing, what's a new week? When does a new week occur? That kind of stuff can be kind of messy. And then I will also provide you the output. This is what the output looks like for the larger file with a temporal interval of 3 minutes. So this defines meals taken together as card swipes within 3 minutes of each other. Right? I think in the paper you read, we used a 4-minute interval, so 3-4 minutes is pretty typical. Are there questions here? All right, let's take a look at the code itself, the template file, just to get you situated. So it looks like almost any other template file you've seen, except that there's a lot more comments. I tried to walk you through this with comments. You'll notice that the stuff is imported as I promised you would be, date, time, and time delta. There are 7 functions in all, 6 utilities, and the driver function. The driver function is written for you, but there's a bunch of these fix-me's in the driver function. They're just strings, and they stand in for stuff that needs to be put in there. So you're going to have to do something with it. For every function, you get a pretty good signature, and in this case, you get some examples. So let's take a look at this. Well, I'll do this on a slide. I have this on a slide in a minute. But you can see the very first function, this looks just like a question of the day, right? I mean, it gives you the signature, it gives you a pass. The second function tells you what it should do. Here's the parse record for that list and what you expect to get back, and you have to do this. Now, this one is hard, not because the code is hard, but because understanding how to use date time is hard. So you have to do some reading. We have a function manage windows, which takes a data structure W, which is a dictionary of sliding windows indexed by location, and an event, and you have to decide which sliding window the event gets added to, and the delta gives me the time interval that I'm interested in working with. So that's the function that maintains the sliding window. So assume we start with no windows at all, and I parse this record and add it with a time delta of 4 to W. It will return to me a list. This is the sliding window for Barnett Cafe, and you'll see there's only one event in that sliding window. Now let's say I process the next element, and I look at W and I see that W, so this is what it returns. W is a dictionary with the name of the location and that list as its value. You return only the appropriate value, but W gets modified. Now let's say I add another record that occurs at 8:12. The first one's at 7:55, and I have a 4-minute interval. Well, 8:12 is more than 4 minutes after 7:55, so what happens is, if we look down here at W, we see that there's a new event corresponding to this event, 8:12, and the old event is gone because it's timed out. Let's say I add another event here that's at 8:15, that is 3 minutes after this previous event, and this one doesn't remove the old event, but just appends the new event to it. So now that window has 2 events in it because they're within 3 minutes of each other. So this gives you an idea of how to deal with how managed windows should behave. The function down here, new week, this is a one-liner, but it is a mess to figure out how to detect that you're in a new week because there may be gaps in the data. Thanksgiving break, for example, is a gap. You need to handle that appropriately. End week, this is the work that gets done at the end of every week. So when you get to a Monday, you want to go through all the data you have so far and compute the meal indices for the people that you then keep track of. And then finally, there's a function that produces the output comma separated value file. Then the driver function, you can see, has a couple of fixmes, but it's largely written and it's reasonably well commented, so it tells you what to expect. Bunch of fixmes in here. Okay? So the first two functions you should write are mindex and parse record. Let's talk about those two functions first. By the way, you really only have like 11 days or something to do this. That's because these aren't that hard, right? Think of them as a bunch of questions of the day. But you can't wait to start on them because you will struggle with date time. Unless you're really lucky and get it right the first time, you're going to have some issues to deal with. And that's going to take some debugging, which can be time consuming. So mindex computes the mindex for an individual based on a dictionary that contains shared meals indexed by student ID. So this is what the input to mindex might look like. So this is the record that corresponds to a particular student ID. Let's say this is my records for student ID 565, which say is me. The value of this record is this dictionary that says I had 5 meals with student ID 26, 1 meal with student ID 104, 1 meal with 117, 8 meals with 55, 5 meals with 142, and 3 meals with 61. So that's the semantics of this record. Now, if you think about it, as I read all the data in the file, I'm going to keep adding to this record, right? As I keep adding meals, these numbers can only grow, and in addition, I'll have new entries with the new people I eat with. So this index starts out empty, this dictionary starts out empty, and grows as I process everybody's meal records. Now, the meal index at this point in time with this particular dictionary can be computed by looking at the values and sorting them from largest to smallest. So let's just do this in our head. The largest value is 8, followed by 2 5s, followed by a 3, followed by 2 1s. So I have 8, 5, 5, 3, 1, 1. And to compute the meal index, I have to use 1 indexing, not 0 indexing. I'm going to start with the 8, and I'm going to ask the question, is index 1, the first position, less than 8? And the answer is yes. Is index 2 less than 5? And the answer is yes. Is index 3 less than 5? And the answer is yes. So far I've got 1, 2, 3. When I get to index 4, the next value is 3, but that's not greater than the index 4. So I stop at the 5. So I get through 8, 5, 5, and here I've gone 1 too far. So that's 8, 5, 5 means my meal index is 3. Right? You just sort them from largest to smallest, and you keep indexing until the index exceeds its corresponding value. That's 1 too far. So your mindex function needs to take this structure and do that simple calculation. That's basically question of the day, quality stuff. Parse record, well, we actually talked about this a bit before. The input here is a list of 3 strings. Now, where do these 3 strings come from? Well, if you were to look at the main scan meals function, the driver function, you'll notice that it opens a file and reads in a line at a time. And the line is just a string. And it splits that line based on the commas. So we get the 3 elements of that line split in order. And that's the input to parse record. And the output is the converted version that looks like this. And again, you're going to have to read up on date time. But otherwise, these are really straightforward. So you should start on these right away. As soon as I meet with the TAs, I'll post the template and the data files. I suggest you get started on this as quickly as possible. And I will suspend question of the days for now. I may give you a chance to submit some of your functions as questions of the day, so I can run them for you. But otherwise we'll skip questions of the day while you do this homework. Any questions? Does it look hard? Yes, go ahead. So it's up to you how you implement it. In Python, it's natural to start at 0. But the value returned, this value here, is a one-indexed meal index. So when you read the paper, it doesn't talk about Python. It says line them up, sort them from top to bottom, and then just count, starting with 1. So you need to return an M index that is counted that way. Internally, of course, you're probably going to use 0 indexing, and then you're going to add 1 at the end, right, as you return a value, for example. Okay? Does that make sense? Anybody else? So it is tricky in this particular application. Sometimes with Python, when you're dealing with data that people are going to look at and interpret, it is not natural for people to think of things in a 0-indexed way, right? So if you were writing this for somebody, think you were writing this for somebody in the registrar's office who's looking at student retention, they don't want 0-index meal indices. Doesn't make sense to them. They start counting at 1. Only we start counting at 0. So since they start counting at 1, you have to make accommodations to make sure that your answer meets their expectations and not just yours. All right? Okay, where were we? We were talking about object-oriented programming. We're going to do some of this today. It will probably be the topic of your last homework assignment. I'll give you a small object-oriented project to implement. I'm trying to decide here. We won't get to it today. We will on Wednesday. We'll start a project together with object-oriented coding. I can't decide if I want to do the Othello. You know what Othello is? The disc flipping game. We could do that. We could play Boggle, which is actually just as interesting if you prefer word games. How many would rather see Othello? How many would rather see Boggle? I think Boggle it is. How many don't really care? Most of you. Maybe we'll do Boggle. Boggle's kind of interesting. We'll also code a user interface for that so we can play Boggle with a mouse, which is kind of a nice thing, just to see how user interfaces work in general. It won't be fancy, but it'll be workable. All right, objects, classes, attributes, and methods. So we need some language here to talk about object-oriented coding. And some of you have already done some with Java, and there's sometimes inconsistent terminology used across languages. So I'll try to define them and use them consistently here. Now, Python is not like Java. Java is a really hardcore, everything's an object kind of language. Python is not like that. Python, as you know, from being type flexible, from variables changing types at the drop of a hat, Python is a pretty flexible language. It's meant to do things fast and dirty. That means that when we say Python has object-oriented constructs, it means you can use Python to write object-oriented code. Python has everything you need to be an object-oriented language. But you don't have to use it exclusively as an object-oriented language, and that means that sometimes people use object-oriented concepts for part of their code and imperative concepts for the other part, or to combine functional, imperative, and object-oriented in this kind of messy, sloppy thing. We're going to try to be purists about object-oriented code when we write code in that fashion in Python. So the organizing element of in object-oriented language is the class. A class essentially is a definition of a data structure combined with a bunch of functions that manipulate that data structure. So excellent examples, which you already know of, are the data structure for string, and all of those great methods that we have for doing things like sorting a string or reversing a string or slicing a string. Those are all methods of the class called string. So many of the data types that you're used to using, dictionary, lists, sets, strings, they're just classes in Python. And that's why we have that dot method notation for the functions that manipulate those data structures. So the main organizing element is a class. Technically, it's called an abstract data type, or an ADT, which is the topic of CS2. So you talk about ADTs for much of CS2. And basically, it tells us what data this instances of this class can store. So in a sense, when I'm using objects in Python, when I'm defining my own object, my own classes, what I'm really doing is I'm typically bundling together a bunch of primitive data types to make a complicated data type. So let's take an example. If I were writing a registrar system for the university, I would want to be talking about elements that are students. And you guys, every student, is really a complicated data structure. They have a student ID number, which is an integer. They have a first name, which is a string. They have a last name, which is a string. They have features like they may have whether they're state residents or not, which is a Boolean for tuition assessment. They'll have a major, which may be an integer that indexes some list of majors. They probably have dates associated with them, date of birth, admissions date, graduation date, all these other types of things. So I would have this really complicated data structure that was really composed of other types of data structures. That's the way you should think about it. So these objects, in this case, an object is an incarnation of a class. A class defines the sort of the template for this object. An object is an incarnation of that template, sometimes called an instance. They bundle these things together and they form a type system. So when I have a student class, an instance of type student is just a new type. So somewhere in the Python, there is a class definition for string and a class definition for list. And every list that you create is just of type list because there's a class called list. And the cool features about object systems is I can define new objects based on existing similar objects. So let's say I wanted to have a list, a new type of list, that was circular, meaning that it didn't have a beginning and an end, but things sort of wrapped around. So the last element came before the first element and you just kept going. Well, I could start with the list definition, the class that's already built into Python, and add some specialty methods to make it behave the way I want it to behave. And finally, the cool thing about objects is that they have associated with them the methods to manipulate that data. And that data, you don't have to share how that data is stored. So I can implement a student object and associate with it all the methods that I use to sort of, put a student on probation. There's a method that says called probation, and it changes the student state so they're on probation. Or have a student graduate, then there's a graduation method. Or have a student take a semester off, there's a semester pause method. All of these methods are associated with the student class. And if one day I decide that the student class was badly implemented, as long as I implement the class with the same structure, meaning the same methods and calling conventions for those methods are available, I can completely rewrite and change the internal representation of student as long as it presents the same set of signatures on its methods and the same behaviors. So it lets me hide what's going on inside, which is really valuable because knowing how something works encourages people to go and mess with how it works. Right? Because, I can take a little shortcut. I can just pull out the third digit of their birth date and that'll tell me something. So I'm just going to grab that. I'm just going to reach inside that object and pluck out the third digit. You can't do that if somebody's going to go around changing the definition. So objects sort of encapsulate knowledge about how the stuff is represented. All right, so let's create a class. My own convention is that my classes, I start them with capital letters. So you probably noticed that I'm careful with function names. I use an upper lowercase or camel case where function names start with a lowercase letter and then subsequent words are upper and lower cases. Python does not allow hyphens in function names, but it does allow underscores. I just don't like typing underscores, so I use camel case instead. You can choose your own convention. For classes, my convention is to use uppercase letters. That way I know immediately what's a class. This defines a class called foo. There is nothing in that class. I can create, whenever I create a class, the name of the class itself is the same as the constructor method for that class. So when you define a class, you automatically get one new method. The new method you get is called the constructor. It has the same name as the class, and it returns a new instance of that class type. So if you think about it, the list class is called list. The automatic constructor is the list function, which converts its argument into a list. It basically creates a new list with the elements that you pass as values. So I can create an A and a B, which are both instances of type foo. I can ask for the type of A, and it will tell me it's of type class main.foo. So what is this? Everybody remember this? This is the module that you're automatically in. It's where you're sort of executing in the read eval print loop. This is the name of my class. So I've got two types, two instances here, A and B, both of class foo. Foo itself has nothing in it. It doesn't really do anything. Now I can attach variables to this instances. So I can by using the dot notation, this is an instance of type foo, a.x equals 3 creates a variable called x that is associated with this instance of class foo. So A has a variable called x associated with it. I can associate a variable called y with A. I can associate a variable x with B, a variable y with B, and I can set it to be the same as A dot y. These are just variables, just like you've used up to now. The only difference is the dot notation with the variables, the thing that comes first is the instance name, is the instance with which I'm associating these variables. And every instance of every class can have its own set of variables associated with them. So after this series of assignments, by is still the value that ay had, which was 4. So ax was 3, ay was 4, bx was 5, by was also 4. I changed ay, it's 6, but by is still 4 because these are separate variables. One lives with A and one lives with B. Okay, so we've got classes and creating new instances of those classes. And those new instances can have variables associated with them that are separate from the variables associated with other instances of that class. Now the next thing that we have to add is some methods. So remember, methods, like in the string methods, are functions that belong to this class. They have access to the internals of the class. And we'll see what that means in a second. You'll notice that when I define a method, I actually define it at the same time as I define the class, and it's indented in the scope of the class definition. So class foo is the name of the class. We'll talk about this later. Colon. And then this thing indented, this is a method for instances of the type foo. Now, there's something funny about this function definition. It sits inside the class definition, but we've seen like helper functions inside other function definitions, so that's not that unusual. But this has a special variable here called self. Every method definition for a class always has as its first variable name self. So every method signature has the self variable as the first element in its signature. That self variable, which is available inside the function, I don't use it here, but self has a value inside this method, will have a special value that we'll see shortly. So this method just simply returns 0. So if I create an A of type foo, and I ask for a bar with no values here, I get back 0. That's just evaluating this function. You'll notice that a bar with no values, Python did not complain that there was a missing value for self. So a bar with no values, normally if you had a function with one variable and you tried to invoke it with none, you would get an error. Python would say, don't have a value for variable self. Didn't happen here. And the reason it didn't happen here is because for a method, whenever you invoke a method, the value of that first variable self will be A. Will be the instance of the object on which it was invoked. So a.bar, inside here, self will have the value A. So the special parameter self refers to the instance of class foo that gets the method invocation. So when you just look at this invocation here, you can sort of think of this as the function bar invoked on A and any other arguments that were added to it. Okay, is everybody sort of clear on this? We'll do an example that sort of helps bring all this together. So here's something a little bit more interesting. I have a class definition foo, a single method called bar, and here I'm going to change self.x, which is the value of the variable x associated with whatever instance I'm calling the bar method on. I'm going to add 1 to it. So let's see how this works. I create a, which is an instance of class foo. I associate the value 5 with a as its x variable. I now create b value with an instance of class foo. I associate 10 to b's x value. When I call the bar method on a, the value of a is the value of self. So self.x refers to a.x. And notice that invoking a.bar doesn't return anything because there's no value returned from the method. But there is this side effect here. Something's changed. And in fact, if I ask for the value of a.x, I can see that it's been incremented by 1. So in this case, this method was able to sort of map a onto self, change a's x value, return nothing, but that change is permanent. You can think of this x value as being inside the container here, inside a container which is the instance of type foo. And the methods reach into the container and change that variable name, or that variable value, and that change is persistent. b.x, on the other hand, has not changed because I haven't invoked anything on b, no method of b, and the bx value is disparate from the a.x value. They're separate, different variables. All right. This is a little dirty for those of you who've done object-oriented stuff before. This notion of adding variables to an instance on the fly like this, it's a little creepy, right? How many of you are uncomfortable with that? Java programmers should be uncomfortable with that. We don't do that. And in fact, in Python, it's not very good practice either. You can do it, but there's better ways of creating variables in objects, which we'll see in a minute. Okay, so this is a little bit of a weirdness of Python. All right, one of the features of object-oriented programming is I can define a class in terms of existing classes. And I can inherit behaviors from my superclass, the class that I started with, so I don't have to re-implement them. So this lets me sort of implement stuff that's almost like something I already have. So we're going to implement a new class called newList, and it's going to, we're going to say it specializes the existing class called list. So right away in this example, we see that the class newList, this separate thing here, is not an argument to the class, but it's a specifier of my parent class, of the class I am most like, the class from which I will inherit. So this class definition doesn't really do anything. It just creates a new object type and says, for all intents and purposes, it's like a list. So if I create an element of type newList and I append I squared to that new list, and then I type A, it sure looks like a regular list. And in fact, it even prints out like a regular list. And the answer is, that's because I've done nothing to change the behavior of its parent class. So I basically made a new copy of this class, but I haven't made any changes to distinguish it from the original parent class. So for all intents and purposes, newList behaves just like list here. In fact, the methods I use, the append method, this is a method of the list class, right? So we have appends that take if A is a list, appending something adds that to the end of the list. In this little loop here that starts with I0, then I append I squared, which is 1, then I append I squared, which is 4, then I squared, which is 9, and I've basically modified the list A. So here we've done nothing different than we've done before, except that I've added this fake name, this fake class. Now this gets a little bit more interesting because I can add variables to that existing list type. So now this tells me a.x, I'm adding a variable x, which its value is 5, to the instance of class newList. And when I print them both out, I get out exactly what I expect to get. So this ability to add extra variables, attach extra instance variables to an instance of a class, can't do that to built-in types, but you can do that by adding a veneer of a new class that inherits everything from that other list type. So this is one feature of inheritance that we can use in Python. Let's take a look at another feature. So here's a new class, new list. It specializes list. I have one new method called longer, and longer returns the length of self plus 1. So when I invoke the method longer, it basically gives me the length of the list plus 1. That's all it does. So if I create a list of type new list, and I do my little appending there, I've got a list of 4 elements. A.longer will return 5, but length of A will return 4. Because A internally is still just a list, the only thing that's different is it has a new method called longer, which returns 1 more than the length of self. So this length here is the same as this length, 4 plus 1, and that's what this returns. So you can sort of see how by starting with a built-in class, you can specialize it and add features to it and make it behave more like the thing you need to have it behave like. All right, let's do a little more here. Same class, specializes list. I'm going to keep the longer method, but I'm going to create a new method called __len__ self. And this method basically returns it's a secret, or prints out it's a secret, and then returns 0. Now, you've seen these underscore methods and names before. What do you associate those with? Where have we seen these kinds of things before? We've seen it in the main module, right? Typically, when you see something encased by underscores, it's internal to Python. This method name is actually the method name that's invoked by the length function. So in Python built-in classes, like list or string, some of the methods carry a syntactic sugar functional variant. So the __len__ method has a functional name which is just a len function. So when you type len of something that's a list, it actually computes the answer to that by invoking the __ len method of type list. So this is the internal guts of what makes len work. So we're going to see what happens with this when I create a new list and I append the usual things to it. And now when I ask for the length of A, this function, which is just syntactic sugar, just invokes this method. Because A is of type new class, we won't get this method associated with list. We'll get this method associated with new list, which prints out it's a secret and then always returns 0. So this method, we say, shadows the original method __ len of the list class from which I have inherited. So you can create methods that specialize the behavior of methods from your parent class. And when I invoke the A.longer method, it invokes the len function on itself, which again invokes this function to compute the length. It still prints it's a secret and returns the value 1 because the length is always defined to be 0. Now this may seem weird in practice, but it's actually quite useful. These are just examples to make you think about how it operates. We're going to get to the next example, I guess, next time because we're at time. I'm going to implement a simple geometric system where you can talk about points in the Cartesian plane, which is a classic example for classes. Yes? I'm sorry, say again? All right. We'll answer this question offline.